Then let's just very briefly recap where we left off yesterday. What we started to talk about was Chapter 7, and Chapter 7 deals with estimation. The majority of our conversation yesterday for Chapter 7 really just evolved around getting a big picture overview of what Chapter 7 is all about. In order to get an idea of what Chapter 7 is about, we kind of try to take a step back and talk about some of the stuff that we've covered already this semester to see how Chapter 7 built on it. And we went and we talked about this picture a whole lot. Just as a quick summary of this picture again, we said we always start with the population, and we're trying to say something about some characteristic of this population. Another way of saying that is we're trying to say something about a population parameter. Here we're just giving the example that U is going to be our population parameter of interest. If we're trying to figure something out about a population parameter, one of the things that we can do is we can take a sample from that population, which is just a subset of the population, calculate out some statistic from that sample here. Obviously, then we would be calculating out the sample average if we're trying to say something about the population average. After we take that sample, calculate out our statistic, whenever we want to say something about a population parameter from our statistic, we say that that's inferential statistics, since we're trying to make some kind of inference. But we also said that whenever we're calculating out the population parameter or the sample statistic, that those are examples of descriptive statistics. That's kind of what we've been doing all semester long. And one of the things that we realized was that whenever we calculate out some sample statistic, chances are that sample statistic is going to be at least a little bit off from our true population parameter. So what we said yesterday is, if we take a sample of 500 people from UNCC, calculate out their average height, chances are that number is going to be really close to the average height of all students at UNCC, but chances are it's going to be at least a little bit off. Then obviously, if you take it to other examples like we talked about for home prices, even those little changes can be very, very significant, right? Once we start getting to the tens and hundreds of thousands of dollars. What we then said is that if we're going to have some sample statistic that we're going to use for inferential purposes, but we know that our sample statistic is going to be off by at least a little bit, well, then let's give ourselves a little bit of wiggle room in our estimate. So we said that if we just calculate out this one number, this one point, that's what we're going to refer to as our point estimate. But once we take this point estimate and we give ourselves a little bit of wiggle room below and a little bit of wiggle room above this point estimate, now we're essentially coming up with an interval where mu could be in. And if this is an interval where mu could be in, then that's what we're going to start referring to as our interval estimate. So one way that we talked about this yesterday was we said, hey, we're trying to figure out the average height of all students at UNCC. Our point estimate could be something like 5'6", where you say, hey, I believe that the average height is 5'6". But knowing that this is probably off by a little bit, we can say, well, I believe that the average height is 5'6", but I'm pretty sure it's somewhere between 5'5" and 5'7". But there, even in that statement, we then introduce another form of uncertainty when we say we're pretty sure about something. So we wanted to start to quantify what pretty sure means. So not only are we going to try to come up with an interval, but we're going to try to express our level of confidence in this interval. So therefore, after we create an interval and we express a level of confidence in our interval, that's why we start calling these things confidence intervals. The last thing that we really talked about yesterday was that whenever we're creating our interval, we're taking our point estimate and we're subtracting something, we're adding something. These were the things that I referred to as wiggle room. The technical term for those were margin of error. So what we're going to really try to focus in on a little bit today is we're going to try to figure out how do we determine what our margin of error is. In this example that I gave up here, I simply just subtracted 1 inch and added 1 inch. How did I come up with 1 inch? Why wasn't it 2 inches? So we're going to start to figure out how to calculate out our margin of error. And we're going to see that the size of our margin of error is also going to determine our confidence level, which was the last vocabulary word that we talked about yesterday. All right, that's a big question overview, or the big concept overview about Chapter 7. Any questions about that before we get into the details? All right, then let's get into some of these details. All right. So I left myself a little bit more space here on the back. Didn't really need that, though. What we're really going to try to focus in on now is this, right? So how do we come up with our margin of error estimates? So first off, let's take a look at what we have down here, right? If we simply just look at this stuff right here, here we have our x bar, just like we have our x bar right here. But here, this symbol right here, it's a plus minus, kind of looks like a plus on top of a minus. What that really represents is it's two separate equations. You can think of this as two separate equations. One, we're going to take x bar and we're going to add something to it. And then we're going to take x bar and we're going to subtract something from it. So we should end up with two separate numbers since we're doing two separate equations, right? Well, whenever we take x bar and we add something to it, we're taking x bar and we're adding something to it. That's going to give us our upper bound of our interval. Whenever we take x bar and we subtract something from it, well, now we're going to come up with our lower end of our interval. Right? Is everybody good with that? All right. So that's what this formula right here represents. It's saying that if we have a large sample, then our confidence interval for the population mean is going to be given to us by this right here. So let's talk about that here real quick. First off, the vast majority of stuff that we're going to do in this class is only going to be to try to estimate the population mean. The only other thing that we're going to try to estimate besides the population mean is a population proportion. Right? Just like at the end of chapter 6, we started to introduce proportions a little bit. We're going to continue to carry that kind of conversation forward, where we're going to spend the majority of our time looking at the mean, and then at the end of the chapter, we're going to introduce proportions, where the vast majority of our focus is going to be on the mean. So here we're dealing with estimating the population mean, but now we also have a large sample. We're saying that it's a large sample. So let's think about this here. If we're looking at means, how do we classify a sample to be large? What is the requirement that we have to have for a sample to be large?
If it's out of the z-score range?
Good. It's when it's 30 or higher, right? Remember the conversation that we had that whenever we're looking at the central limit theorem says that if we're dealing with averages, we need to have a sample size of 30 or greater. Whenever we're dealing with proportions, what do? Yeah, good. Try to find that interval between 0 and 1, right? Awesome. So we're going to see that we're going to look at that a little bit later, but for the time being, we're simply just looking at sample means, so we need to have a large sample. So all that this is really referring to, as it says right here, is that a sample is considered to be large whenever n is greater than or equal to 30. All right, everybody good with this so far? Now, if we look at these formulas, we already know every single component of this formula. We know what x bar represents. It's the sample average. We know that we have some kind of z-value here. Here the z-value has a subscript, and we'll get to that what that subscript here means in a minute. But then we're also looking at sigma, which is what? What does sigma stand for? Population standard deviation. And what does little n stand for? Our sample size, right? So we know what all those things are. We're putting them together in order to come up with some confidence interval. All right, then let me ask you guys this right here. We're taking x bar, and we're adding this to it, and we're subtracting this from it. Right? What I just put in the box, we're both adding to x bar and subtracting from x bar. We learned a vocabulary word then for what I just put into a box. What's the vocabulary word for this thing that I now put in a box? It is the margin of error. Awesome. So whenever we take our points estimate and we add something to it and we subtract something from it, we're creating our interval. The portion that we're adding to it and we're subtracting from it is what I first started referring to as our wiggle room. But now we're going to call this thing our margin of error. Our margin of error, we're going to use this symbol capital E to signify our margin of error. And all that this down here says is that this is our margin of error. E is equal to that portion that we're adding and subtracting, which is our margin of error. Awesome. Everybody good with this so far? All right. So basically what we're going to do now is this. We're going to be given some problem set up. They're going to tell us what a sample average, what our sample average is. They're going to tell us a sigma value. They're going to tell us a little n, a sample size, and they're going to give us something here that we can figure out our z value, right? So let's figure out what this z value component is right here, because there's a slight little change to this, because we have now a subscript to it. So let's take a look at what our subscript means. All right. Yesterday, one of the things that I pointed out, or I just very, very, very briefly mentioned, but I definitely want to point out here again today, is this last sentence right here, where it says, it's very important that we remember that our confidence level is given by 1 minus alpha. Right? Our confidence level is given by 1 minus alpha. It's extremely important to remember that your confidence level is 1 minus alpha. It's not written on your guys' formula sheet, but this is a very, very, very important concept. You have to remember that your confidence level is given by the formula of 1 minus alpha. So what does this mean? Again, as I said above here, we're going to come up with some interval. And that interval that we come up with, we want to express some kind of level of confidence. Just real quick to put that into words again. If I say, hey, I think that the average height is 5'6", but I'm 90% confident that the average height is somewhere between 5'5" and 5'7", right? So now I assigned a new number to that. I said I'm 90% confident. I just told you my confidence level, and that's 90%, right? So let's take a look at this here. If I say that my confidence level is equal to 90%, how big is alpha? 0.1, right? Alpha is equal to 0.1. How did you get that? Well, if you're saying that confidence level is the same thing as 1 minus alpha, then 1 minus alpha is also equal to 90%. Add alpha to both sides, subtract 90% from both sides, right? And then convert it to a decimal place. You're going to have alpha is equal to 0.1, which is just the same thing as 10%. Right? Is everybody good with that? So from the simple expression of I'm 90% confident that, we can now figure out what alpha is. Doesn't matter what it is, right? If I tell you that I'm 95% confident, how big is alpha? 5%. If I tell you that I'm 70% confident, what's alpha? 30%. Everybody get the gist? All right, cool. So that alpha, though, is extremely, extremely, extremely important. So let's go over to this next page now. Because we're trying to figure out what our z sub alpha divided by 2 is, right? So let's just do that quick little exercise again. If I tell you that I'm 90% confident, and you already could tell me that my alpha level is 10%, well then what is my subscript going to be? I have alpha divided by 2, so now I have 5%, right? So what we're essentially looking for then is a z value that corresponds to 5%. I see some people going, right? Because now what we're doing is we're putting a percentage with a z value, and you guys know how to do that, right? If you have a percentage and you want to find a z value, what do? You go to that table. Where do you look on the table? In that body of the table, right? Like in the big section right in the middle. You find that percentage and then you follow it out. So now what we can do is this. I can give you any level of confidence. You can figure out what your alpha divided by 2 is. That's going to give you a percentage. You can find that percentage in the table and then find the z value. Everybody good with that? Bam! Now we know what z sub alpha divided by 2 is. Everybody good with that? All right. So if we're given a level of confidence, and we're given a sample mean, and we're given sigma and a sample size, we have everything that we need to know to calculate out our confidence interval. Right? Is everybody good with that? All right. If, for some reason, we don't know sigma, right? In this first equation right here, it says we know sigma. Well, if we know sigma, we can put sigma right here in the numerator of this equation. But if we don't know sigma, if sigma is unknown, well, then we can't put sigma in the numerator of the equation. We don't know sigma, right? So then what do we need? We need to have a sample standard deviation instead. So they're either going to give us a population standard deviation, or they're going to give us a sample standard deviation. Either way, so far, it doesn't really matter. Whatever standard deviation they give us, we're going to put that up in the numerator. Right? They're only going to give us one or the other. Whichever one they give us, we're going to put that up in the numerator. All right. Everybody good so far with what these formulas are and where we're going to be using them and starting to get an idea of how we're going to apply them? All right. Then let's start applying them. Find the number z sub alpha divided by 2 needed in the construction of a confidence interval when the level of confidence is 95%. All right, so let's do this first one together. We know that our level of confidence, which I'm going to start abbreviating as C alpha confidence level, is equal to 95%. And we're trying to find z values. So what's the first thing that we're going to do? Good. We're going to figure out what alpha is, because we know that our confidence level has a formula 1 minus alpha. Then alpha, we're simply just going to take 100% minus 95% in order to find out that this is 5%, which is just equal to 0.05. So now we know that our alpha is 0.05. In that previous page, in the formula that we just got done looking at, was it z sub alpha? No, what was it? Alpha divided by 2. So now we need to know what alpha divided by 2 is. And I know that my alphas sometimes start looking like my 2's. But this is alpha divided by 2. So then alpha divided by 2 is obviously going to be 0.025. Everybody good with 0.025? All right. Now we want to know a z value. We want to know our z sub alpha divided by 2, which is just a z value that corresponds to 2.5%. And if you want to find the z value that corresponds to 2.5%, what z value is that? 1.96. Or if you really look at it, if you're trying to look for 2.5%, we're going to say that it's negative 1.96. Right? Right? Is everybody good with this? All right, Rachel's over there going, wait a second here. You almost threw me for a loop. I thought I was on the same page because I didn't have this negative up here real quick. But let me show you guys why we're getting to the point now where that negative symbol doesn't really matter. All right. Why is it not going to really matter here? What are we going to do with this number? Add it and subtract it. Right? If we go back to our formula, right here, we're going to take this z sub alpha divided by 2, which we just found out. We're going to multiply some other stuff to it. But after we multiply some other stuff to it, we're going to add it and subtract it. So if you're adding and subtracting a negative number, or you're adding and subtracting a positive number, one way or the other, you're still going to get the negative portion of it, and you're going to get the positive portion of it. So therefore, what we're going to do, the convention is, especially for your textbook, which accompanies this class, the convention is that whenever we're referring to the z value, we're just going to refer to it as a positive number. Knowing that, the only reason why we're going to do this is because we're going to add it and subtract it. Everybody go with this again?
So we're not done with that little sheet, are we?
No, we're not. No, we're not going to be done with it for the rest of the semester.
It's behind.
Yeah, we're going to be using that for quite some time.
So at this time, no matter if you get a positive, so if you get a negative, you always turn into a positive. If you find a positive value, you just keep it as well.
That's right. Good. Yep, so if you have a positive or a negative, just by convention of this class, it doesn't really matter what you use. All right, is everybody good with this 1.96 right here? All right, what I want to do is I want to take a step back, and I want to go back to the space that I have at the top of this page. So I left this space right here to illustrate exactly what we just got done doing with the positive or negative. Because now what we're doing here is this. We're using our normal distribution, right? Again, we're dealing with z values, so we know that we're dealing with a normal distribution. But now what we're doing here is this. We're looking for z values. Here, this z sub alpha divided by 2, such that beyond this point, we only have alpha divided by 2 left. Right? So on this side, we only have alpha divided by 2, and on this side, we only have alpha divided by 2. So what we're looking up currently is we're just looking up this left-hand side right here. What we're doing is we're saying this. Hey, I'm given some confidence level. And I know my confidence level is equal to 1 minus alpha. From this, right, I'm going to be given some percentage. I'm just going to use a random percentage, the one that we almost got done doing. We're going to get to this one here in a second. But here, then, we're going to know that alpha is equal to 10%. What we're essentially then doing is we're saying, okay, we want to find our z value that corresponds to alpha divided by 2. So then alpha divided by 2 is going to be equal to 5%. Since we're now taking this to the z table, right, we have a percentage. We're taking this to the z table. The only time that we can use the z table is when we have what? A bell-shaped symmetric graph, right, whenever we have our normal distribution. So once we start taking this percentage and we start using it as a z table, now the next step is to take it to the z table. So this is here for our z graph. But what we're essentially then saying is that whenever we're looking up an alpha divided by 2, whenever we're finding a z value for this alpha divided by 2, we're essentially just finding the percentage of this graph, right here, being 5%, and we're looking up the z value that corresponds to that. Is everybody following along with me so far? You get it? Cool. Right? Is everybody good with this? What's happening here? So once we look up this percentage in our z table, we're saying that we want to look up this z value right here. But once we look up this z value for that 5%, all we're just saying is that from here on down, we have 5% of our table. Well, this right here has to give us a what? A negative z value. So this thing right here has to be negative. Now, the only thing that your textbook does is it says, negatives. What we can do is we can just use the positive. Well, why is this the case? Well, if we split up alpha into 2 pieces and we put half of alpha over here, well, naturally speaking, then we have to have the other half of alpha over here. Right? So therefore, if we have the other half of alpha over here, well, then this is just going to be a positive z value. All that we're essentially doing then, whenever we create confidence intervals, is we're going to start to establish a confidence interval that begins right here. I'll make this into somewhat of a square bracket so you guys can see it. It starts right here, where we're going to be adding and subtracting something that's based off of z values, right? This picture isn't 100% correct, but it should give you guys an idea. What's going to be this point right here in the middle? The mean is going to be our x bar, right? Because we're going to take our x bar, we're going to subtract something from it, we're going to add something to it, which is going to give us our interval. And if we create that interval now, that's going to be using our z values, which is what we're getting for something right here. Okay? So this is like the more theoretical picture of what we're really doing with this adding and subtracting and multiplying and stuff, is we're just creating an interval. And our confidence level is telling us how much space we want to have on this side right here. Okay? So let's think about this here for a second. This was for 90%, right? We had this much space, right? Here we have 5% on this side, we have 5% on this side. If I tell you that I have a confidence level of 99%, how big is alpha? 1%. So therefore, how much is just going to be in one of these shaded regions? Like 0.5%. So So is my interval getting smaller or is my interval getting bigger? Bigger, right? Because now over here I don't have 5%, I have a 0.5%, and I have a 0.5% over here, so I have to be going bigger, right? So whenever your confidence level goes up, your confidence interval is getting bigger. Right? Does that make sense? Whenever your confidence level goes up, your confidence interval is getting bigger. Now, let's take that back to the example that we talked about last class. If I told you that I thought the average height of all students at UNC Charlotte was 5'6", but I was really, really confident that the average height was somewhere between 5 feet and 7 feet, you would say, right, like no crap. Right? Is everybody good with that? No crap it's between 5 feet and 7 feet. You're giving me this huge interval. You're giving me this huge, huge, huge interval. So what we're doing is that we're not saying here that we're somewhere here. We're getting like this huge interval where like the cutoff is way over here and the cutoff is way over here. That's why our alpha is practically 0. That's why I'm saying I'm 100% confident. Right? Is everybody good with that? But we're conveying absolutely no information with it whatsoever because you're really, really confident in something that's just completely obvious. Right? All right. So that's basically what's happening right here. Is everybody good with that concept? Because you're definitely going to see that concept again. Right? Which means what? Like start in your notes, write like this is going to be on the test. Yeah.
Back to the Z that we did over here.
Yeah.
It says plus will always be positive. So on the test, will it always show a positive number, never a negative number?
Great question. It's just a convention that we always use this number right here as the positive value. It really doesn't play that big of a role until later in Chapter 7. Because what we're going to start doing, is it Chapter 7? Yeah, it's Chapter 7. No, it's Chapter 8, sorry. Anyways, later on what we're going to do is we're not going to have two cutoffs. We're not going to be creating an interval. Instead, what we're going to do is we're just going to create one estimate. So we're just going to have one cutoff. And there it's going to depend whether or not the cutoff is on the right-hand side or it's on the left-hand side. Right? You good with this? So if it's on the left-hand side, we should be using a negative z-value. And if it's on the right-hand side, we should be using a positive z-value. But the way that we're going to write the formula is just plus z times something. So we're just going to always write it as plus something, plus something, plus something, where sometimes you're going to be plugging in a positive value and sometimes you're going to be plugging in a negative value. Right? So that's a little bit of a longer answer for it to... You're never going to be asked specifically to provide just this number. You're going to have to use this number. And the way that we're going to write our formulas is you have to know which one of these to use, right? Let me backtrack on something that I just said before. We're not always going to use plus something. We're going to use plus something, and then we're going to use minus something. So we're always going to plug in a positive z value into it. Right? But let's worry about that once we get to chapter 8. All right. Take a minute for yourself and see if you can find a z value that corresponds to a confidence level of 80%. Anybody need a little extra time? All right, so then what we're doing here, if we want to put this into pictures, right, we're saying that our confidence level is equal to 80%.
So here, what we're going to do then is we're going to say that in between these two cutoffs, we have a confidence level that's 80%. Well, we also know that this is equal to 1 minus alpha, so therefore alpha should be 20% or 0.2. And now if we divide alpha divided by 2, we're going to say that we have 10%. Another way of saying that is that we're going to put 10% over here, and we're going to put 10% over here, which is just equal to alpha divided by 2. Now what we're trying to do is we're trying to find these z values. So here we're trying to look up these z values right here. And if you look up 10% in your z table, what z value do you get? Negative, or just positive 1 point. 1 point. What is it? 1.28. Is everybody good with 1.28? Anybody need help finding 1.28? All right. So then our z value is negative 1.28. Where obviously here on the right-hand side, it would be a positive 1.28. And over here on the left-hand side, it would be a negative 1.28. All right. What about C? Take a minute for yourself and see if you can do C by yourself.
B
Yep.
has the 0.1, like the something over 2. Is that an X or a 0?
That's an alpha.
Oh,
So we're taking 1 minus alpha, and then here then alpha, if we have 80% is equal to 1 minus alpha. If you solve for alpha, we're going to add alpha to both sides and subtract 80% from both sides. So that's then going to give us alpha is equal to 0.2.
Okay.
Right? And then what we're doing right here is we're taking alpha divided by 2. So then if you take 0.2 divided by 2, you get 0.4.
Okay.
So what we're basically saying is that we have 80% of stuff right here. Anything that's not in here is equal to alpha.
Mm-hmm.
Then we're splitting alpha up into our two regions. So we have alpha divided by 2 right here and alpha divided by 2 right here.
Okay, so you're always going to split them up?
Yeah, whenever we do confidence intervals, we're always going to
Okay.
split.
Okay, cool.
So for all of chapter 7, we're always going to split.
Okay.
Yes.
So is it because the z value is always plus or minus, that in the formula it's like plus or minus c?
No.
Okay.
Let me talk about that so everybody can get the answer to that. Good question. All right. So does anybody need a little extra time for C? All right. So once again, our confidence level is equal to 90%, which is equal to 1 minus alpha. Therefore, alpha is equal to 10%. And therefore, alpha divided by 2 is equal to 5%, or 0.05. So what we're doing then is we're putting 90% of our graph between our cutoffs. So here we have 90%. Then over here we have alpha divided by 2, and over here we have alpha divided by 2. So therefore, if in here we have 90%, and it's a symmetric distribution, then over here we're going to have 5%, and over here we're also going to have 5%, or 0.05. What we're trying to do is we're trying to find these z values that correspond to alpha divided by 2. Right? That's the whole objective of this. We're just practicing alpha divided by 2 z values. And if you look up a z value that corresponds to 5%, what's the z value that you get? Good. So here's 1.64. All right. If you look at the z value for 1.64, what's the percentage that you get? Good. 0.0505. If you look up the z value for 1.65 or negative 1.65, what do you get? 0.0495. Right, is everybody good with this? Can I borrow somebody? Can I borrow your seat? Yeah. I'm woefully underprepared today. All right. So if we go to negative 1.64, we're right here. And if we go to negative 1.65, we're right here. Right? Is everybody good with that? But what are we looking for? 0.05. So technically speaking, where is 0.05? It's like literally right in the middle. right? So you can use 1.64, or you could use 1.65. Those answers are going to give you stuff that's slightly different, but you're really just down into like the third or fourth decimal place. Or if you want to, you can use 1.645, which is right in between 1.64 and 1.65. Right? We've done this before in the past, where we're saying, hey, we're just going to choose the value that's literally right in between these two. And the value that's right in between these two is 1.645, right? Now, technically speaking, that's theoretically not correct, right? Because what are we doing here? We're creating an average in between these two. And whenever you create an average, what are you doing? An average is really nothing more than a straight line. Right? You take like the average of two numbers, you're creating a linear relationship between those two numbers. And is our normal distribution a linear relationship? It's not a linear relationship. So what we're doing here is we're saying this. We understand that the graph is not a line, but it's a curve. But if you get really, 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 really close to it, and you blow it up, well, once you're really, really close to it, it's getting closer to just a straight line in between those two points, right? That if you're not using a straight line, if you blew this up into like 10 decimal places, you're going to see that these things are different, that it shouldn't be like halfway in between these two. But we're not going down to like 10 decimal places.
So when they're equal distance from each other, there's not like a set preference of higher or lower?
No.
Whichever one you want.
Whichever one that you want. What we're going to start using here, I'm going to start to introduce 1.645. It doesn't matter whether you use 1.64 or if you use 1.65. But later on in Chapter 7, I'm going to show you guys a new table, and that new table is going to give you to 3 decimal places. So on that table, it's going to say 1.645. So I'm just trying to warm you guys up to the fact of why does it say 1.645. But we'll get to that table probably tomorrow. All right. So, thank you, sir. So everybody's good with 1.645? All right. Then I think you guys are starting to feel pretty comfortable with these, right? Let's do this last one together. You have a confidence level of 99%, which is going to give us 1 minus alpha. So therefore, alpha is equal to 1%. Alpha divided by 2 is equal to 0.005, or a half of 1%. I could draw a similar graph up here, but if you looked up the z-value that corresponds to alpha divided by 2, we're looking for a z-value that corresponds to 0.005. And if we look this one up, we get 2.57. It's really right in between 2.57 and 2.58, right? So we could use 2.575, but which one is it closer to? Is it closer to 2.57 or 2.58? Is it equidistant again? All right. What we're going to see here then in that table that I'm going to introduce next class is it's technically 2.576. But just like we had for Part C, it doesn't matter whether or not you use 2.57 or 2.58. The answer choices that you get are going to be really similar, but as we're going to see tomorrow, the technical value for this is 2.578. All right. You guys feel comfortable now looking up z sub alpha divided by 2s? That's really the only new symbol that we need for confidence intervals, right? We need to know what that plus or minus stands for, which we talked about, and we need to know how to look up z sub alpha divided by 2s. All right. So, this is right here. This is extremely, extremely, extremely important for you guys to know for confidence intervals. All that we've done so far is we've looked at large sample estimates for the population mean. Whenever we're looking at large sample estimates, where are we up here on this table? Just the top, just this portion right here, right? Because here we have large samples. We have n greater than or equal to 30. If we're down here where we have small samples, another requirement that we have to have is that our population needs to be normally distributed. We haven't gotten to that yet, so let's just stick up here. Whenever we're dealing with large samples, then if you look at those two equations that we had on the previous page,
have that sigma is known or sigma is unknown. So here we either have sigma is known or sigma is unknown. But the only thing that we're ever going to use right here is we're always going to use z sub alpha divided by 2, which is what we're saying right here. Right? And that's what we practiced now a couple times. You guys are good with this. We don't need to know what's over here in this other column. What we're going to start doing here in a couple of minutes is we're going to say, okay, what happens if we don't have large samples? If we don't have large samples, then we have small samples. And when we have small samples, again, we're going to be dealing with the case of whether or not sigma is known or sigma is unknown, so just like up here. Again, if sigma is known, we're still just going to use our z sub alpha divided by 2. Nothing changes there. But, and here's the important thing, whenever we have small samples and sigma is unknown, now we're no longer going to be using z sub alpha divided by 2. We're going to start using t sub alpha divided by 2. And t sub alpha divided by 2 is a different kind of distribution. So let's take a look at that different kind of distribution so far. Right?
Should we memorize this?
So I usually tell my students that yes, you should memorize this. However, what I've done for you guys, since this is a summer class, is I gave you guys that formula sheet. And this is technically on the formula sheet. So let's take a look at that formula sheet. All right, so I said I was woefully underprepared. However, at least I have a formula sheet with me. If you go to the back page of your formula sheet, and you go to the back page of your formula sheet, what I introduced to you so far is essentially this stuff right here. We're doing inference about a single population mean.
We have not looked at this column at all yet, this test statistic. That's what we're going to start looking at in Chapter 8. So this is like our Chapter 8 column, so you just pretend like it's not there. Right? What we've done so far is we basically said that, hey, here we've looked at these two formulas. These two formulas were on that previous page that I keep referring to, right? Whenever sigma is known and sigma is unknown. And the only difference between these two things is that one of them has a sigma and the other one has an s up here in the numerator. Well, obviously, just like we said before, if sigma is known, we're going to put sigma in there. Whenever sigma is unknown, we can't put sigma in there, so we're going to use s. And what does s stand for again? Our sample standard deviation. Good. So if we don't know our population standard deviation, we have to at least know our sample standard deviation. Then basically what we said down here too is that, again, we're in that scenario right here. The only thing that we're really just changing right here is we're changing our z and our t sub alpha divided by 2. So the only difference between what's on your formula sheet and in that box that I just gave to you is that box that I just gave to you only includes this section right here, whereas the formula sheet spells out the entire formula.
Okay.
So the easy answer to your question is you do not necessarily need to memorize it for the summer class, but if you do memorize it, you're going to be able to go through these questions a lot quicker.
Okay. Thank you.
Yep. Awesome. All right, so here's this. Let's take a look at the t distribution, where we're getting these t's from. Then once we get through this page, we'll start doing some word problem examples. All right. So the only time that we can ever get down to that formula that uses the t in it is only when we have small samples. Right? It's like the very, very bottom part of that table, that formula table. And to get down to the bottom of that formula table, the only time that we can get down there is if we have small samples, right? Everybody good with that? So therefore, whenever we have small samples, that's why here we're now talking about getting to section 7.2, where we're talking about small sample estimates for the population mean. Again, we haven't gotten to population proportions yet. We're still dealing with population means. But now we're getting away from having large samples to small samples. So whenever we're looking at the population mean, what does it mean to have a small sample? Strictly less than 30, right?
whenever we have sample size that's less than 30, we're going to start using t-values, and therefore we're going to start getting these t-values from our t-distribution. Right? Instead of using a normal distribution, which is sometimes also referred to as a z-distribution, we're now going to start looking at t-distributions. All right. So technically speaking, these t-distributions, they're called students' t-distributions. And the students' t-distribution, the reason why it's called students' t-distribution is not just because it's for students. It actually has a pretty funny background story. The person who came up with students' t-distributions was a brewer, a chemist, at a brewery. It was at the Guinness Brewing Company, right? It was like back in like the 1800s. So what would happen was they hired him as a chemist or to do statistical models on their batches of beer, right? He would go out and he would sample batches of beer, and then they would ask him to do different calculations on this to make sure that it was optimizing their brewing of Guinness beer. Now, what he started to realize was the batches that he was taking, and this is why I always wonder if he was drinking these batches, right? The batches that he was taking, he would never take more than 30 batches. He would always take less than 30 batches. But he started saying, wait, in order to make sure that the central limit theorem applies, right, to make sure I have my bell-shaped distribution, I need to have 30 or more. So he said, apparently, like this is how I always imagine, like he's drinking beer, doing some statistics, right? For some reason, that was a good idea to him. But he said, hey, let me start to take a look at these distributions if we don't satisfy the central limit theorem. We're taking less than 30. Okay? So what he started to realize then was that what happens is if you have a sample size that's small, you still have a bell-shaped and symmetric distribution, but what it looks like is that somebody kind of took the top and they kind of pushed down on it. So it's just shorter, and what happens whenever you push down on the top, the tails, they just kind of got fatter, right? But then as your sample size increased from like 5 to 10, then you kind of think like somebody's pulling up on this. Once you got to like 20, they're up higher. Once you got up to like 25, you're even higher. And once you got to 30, well, that's when the central limit theorem came into play. And that's when your t-distribution was really, 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 really darn close to your normal distribution, right? So that's where he said, hey, you can still imagine that you're working with a bell-shaped and symmetric distribution when you have less than 30 as your sample size. But it's not quite a normal distribution like the one that we have. It's really just shorter and fatter out in the tails, right? Now, the cool thing about this was he was doing statistics, drinking Guinness beer or whatever, and then he wanted to publish these results. He's like, oh, this is significant. Like, people can use this whenever they're not taking more batches than 30. And he wanted to publish it, but what was going to happen was, because he was an employee of Guinness, they were going to claim that information as proprietary to their company. Right? They were going to claim it as their own, right? Which is reasonable. You're paying somebody to work for you. They come up with something while they're working for you. That should be the property of that company. So what he did was he goes, after a couple of beers, he goes, no, screw it. These are my results. He published these results, but not under his own name. He just used his surname of student, right? So that's why all these things started to come out as students' distribution. He started calling them t-distribution. And the name stuck, so now they're just known as students' t-distribution. Right? All right, so that's a little bit of background information on that. But whenever we look at students' t-distributions, if we go back to this page that we had just before, if you look down here, the students' t-distribution, right, whenever we get down here, we have these things that are called degrees of freedom. Well, degrees of freedom, what the technical aspect for degrees of freedom is a little bit theoretical, and we don't need to really know that for this class. The only thing that you really need to know for this class is that when we're calculating out confidence intervals, that degrees of freedom is equal to little n minus 1. That is something that you have to remember, that degrees of freedom is always equal to little n minus 1. But again, it's on your formula sheet. If you look to the right hand, the far right-hand column of your formula sheet, it says right here in this column that degrees of freedom is equal to little n minus 1. So, degrees of freedom is equal to little n minus 1. So, let's come back over here to this graph right here. Your degrees of freedom is equal to 25. So therefore, your sample size is equal to 26. Right? Because it's little n minus 1. So the way that we get from 26 to 25 is by subtracting 1. What is your sample size going to be for 15? 16. And then obviously for 5 degrees of freedom, you're going to have a sample size of 6. So if you wanted to extend this graph, and you wanted to include the normal distribution, technically speaking, it would be the standard normal distribution. But what we're essentially going to get then is we're going to get something that's really, really close to this last graph. It has a little bit thinner tails, and it's just slightly above here. And then this last one that I'm drawing in, this right here is going to be our normal distribution. So like I said before, as our sample size increases, 6 to 16 to 26, and for our normal distribution we have to be at 30 or greater, we start to get closer and closer and closer to our normal distribution. All right. So then that's the last thing that we really need to know to calculate out our confidence intervals. What we're always going to see is, are we dealing with a large sample or are we dealing with a small sample? If we're dealing with a large sample, we're always going to be using z's. If we're dealing with a small sample, the only time that we're going to use z values is whenever we know sigma. If we don't know sigma and we're dealing with small samples, now we're going to introduce these t things. Right? Is everybody good with these concepts? The practice problems for these ones where we have t values in them, that's what we're going to start to do next class. But starting today in this class, now we can go back a page in the notes. I know I skipped a page in the notes earlier. We can go back a page in the notes, and we can start doing word problems for confidence intervals. All right. So what I first started off the notes with was a word problem where it's literally just giving you the bare bones for the stuff that you need to know, right? Like it literally just says a sample size of 49, blah, blah, blah. If you go down here to number 2, you can start seeing that it's a similar type question. I'm just making it to a more traditional word problem type where I'm just adding some flowery stuff in here that says, like times of room service and stuff like that. But the overarching concept is that we still just want to boil it down to the bare bones information that it's given to us right here in this first example. So let's do it. A sample of size 49 has a sample mean of 35 and a population standard deviation of 14. Construct a 95% confidence interval for the population mean and interpret your results. All right. The first thing that we're always going to do, I don't know why this is so crooked, but it's bugging me. The first thing that we're going to do is figure out where we are in our table. Right? So because you guys have access to this formula sheet, we'll use this formula sheet. But like I said before, this formula sheet is really similar to what's already in our notes. In this problem, do we have a sample size that's greater than or equal to 30? It's greater than, right? What's our sample size? 49. So we know that we're going to be up here. In this problem, do we know sigma? Right? Again, what does sigma stand for? It's the population standard deviation. Now it's going to start to become important that we can distinguish between sigma and S. Right? Between our population standard deviation sigma and our sample standard deviation S. Doesn't really play a big role whenever we have a large sample size, but whenever we have a small sample size, it's going to determine whether or not we're down here or up here, and it's going to determine whether or not we're using z values or t values. Right? All right, but we're still up here. So we have a large sample size. So the first question that we're always going to try to answer is n greater than or equal to 30? And we said yes. And we said, is sigma known? And to this we also answered yes. So therefore we know that here we're going to be using
z values. That's the most important thing, that we're getting the z values out of this.
All right. Let me phrase this a little bit differently.
The two questions that we're always going to be asking ourselves are these two questions up here, because that's the two questions that we're getting from our table.
If you answer yes to at least one of these questions, then we're going to have a z value, right? Does that make sense?
If we answer yes to at least one of these questions, then we're going to be using z values and not t values. All right, let's see why that's the case.
If I say that I have a sample size greater than or equal to 30, what part of the table am I on? The top part. I'm up here. If I'm up here, do either of my formulas use a t value? No. So therefore, if I answer yes to this question, is n greater than or equal to 30, I have to use z values. Everybody good with that? The second question is what? Is sigma known? If I answer yes to sigma is known, then I'm either right here on the table or I'm right here. If I'm right here or right here, do I ever use t values? No. So therefore, I just need to answer yes to one of those two questions, and I know that I'm going to be using z values. Right? Is everybody good with that? I just need one of them.
But we're always going to ask ourselves both of those questions until we get comfortable with it. Because like Amelia asked today, you could just memorize these, but if you start to feel comfortable with them, you don't have to memorize them, so we're just going to keep asking ourselves these two questions, knowing that we just have to answer yes to one of them. Right. So we know we're going to be using z values. So therefore, here the formula that we're going to use is we're dealing with the population mean. The estimate, therefore, for our population mean is going to be x bar. Right? That's going to be the sample statistic that we're going to use to estimate our population parameter. And for this, then, we're going to use plus or minus. We just determined that we're going to use z. So z sub alpha divided by 2 times something. What are we going to be multiplying this by? What always goes down here in our denominator? Square root of n. But now what symbol am I going to use for my numerator? And why am I using sigma?
Because we know sigma, right? Here we know sigma, so therefore we are going to use sigma. If we did not know sigma, what would this become? Yes. All right.
Now, the one question that I always get is, how do I know that I know the population standard deviation? It might be a little bit obvious in this question right here, but as we start going into other word problems, it might be a little bit less obvious to you. Here's the one thing that you can rely on.
It needs to say that the standard deviation is coming from a population. It needs to be explicit about it, right? It can say, hey, you have a population with a mean of 5 and a standard deviation of 2. Well, there it's saying that your standard deviation is coming from the population. If it says you have a sample with mean 5 and standard deviation of 2, well, now you know that your standard deviation is coming from a sample, right?
So your telltale sign of whether or not you're using a population is that you have to have the population word in there whenever it's talking about the standard deviation. All right. So therefore here we do know sigma. Everybody good with this stuff so far? All right. What is x bar in this problem? 35. We have a sample mean. X bar is the sample mean. We have 35. I'm going to skip z sub alpha divided by 2 here for a second. What is sigma equal to in this problem? What is our sample size in this problem? Everybody good with these three numbers? You should be, right? These are like coming from like chapter 1 and 2. Therefore, the only thing that's new in this formula is what we practiced like at least 5 times at the beginning of class today, and all of you said that you felt comfortable with, which is just finding z sub alpha divided by 2. All right? So take like 30 seconds for yourself and see if you can find z sub alpha divided by 2 for this problem. Anybody need a little extra time? So you have a 95% confidence level. How big is alpha? 5%. Therefore, alpha divided by 2 is 2.5%. If you look up a z-value that corresponds to 2.5%, you get negative 1.96. And what we're always going to do is, we're just by convention, we're just going to put 1.96 right here. Because again, we're just adding and subtracting, whether we're adding and subtracting a positive or negative number. It's still just adding and subtracting, same thing as same. Those two things are same. Right? Everybody good with this setup? So literally now, all this is just arithmetic. Technically speaking, we have two problems up here. We're going to calculate out this portion right here. What's this portion right here called again? That's our margin of error. We're going to calculate out our margin of error. We're going to add that to 35 to give us the upper bound. We're going to subtract it from 35 to give us the lower bound. And voila, we have an interval. So what this should come out to be is this should be 35 plus or minus, 3.92. So 3.92, this right here is our margin of error E. And if you take 35 and you subtract 3.92, you get 31.08. And if you add 3.92, you get 38.92. And there we have our interval. Now, sometimes you'll see these intervals with round brackets. Sometimes you'll see these intervals with square brackets, right? Let's talk about that here for a second. Does it matter whether they're round or they're square? Why not? Good. And what was that reason? Good. It's irrelevant if we're adding or subtracting one single value. And why is that the case? Because here, if we're using z values, we know that we're using our normal distribution. And our normal distribution is a continuous distribution. So therefore, we're using a continuous random variable. Right? So therefore, it doesn't matter if it's square or round. I think your textbook primarily uses round, but it really doesn't matter. All right. So here's our intervals. Everybody good with this interval? How to get this interval? So therefore, then the only thing that we still need to do is provide an interpretation. And our interpretation is this. It's going to say, we are 95% confident that the population mean mu is in the interval. We just calculate it out. Here I'll write in round brackets. 31.08 to 38.92. We are 95% confident that the population mean mu is in the interval where we just calculated out 31.08 to 38.92. Scoot up. So the wording of this interpretation I wrote down here very, very specifically. You can definitely come up with variations of this right here, but I recommend that you remember this particular interpretation. And the only thing that you're ever going to change out in this interpretation is this. You're going to change out your confidence level, because here we were 95% confident, but we could have easily had a different problem set up where we were only 90% confident or 80% confident. We're still looking at the population mean, but like I said, later on we're going to deal with the population proportion in this class. So the only other thing that you could change out then would be mu. And then obviously this interval that we calculated out, we could be coming up with different numbers for that interval if we were just having different numbers in the problem.
So therefore, in this interpretation, the only thing that you're going to really ever change out are those three boxes. So therefore, if you just remember this sentence and you have to provide an interpretation, if you just write down this sentence, then you just have to plug in those changes for the sentence in those boxes, right? The reason why I recommend this is this. A lot of times people try to interpret these results, but the interpretation that they give is completely wrong, right? There's a fundamental thing that they always say that's wrong. And primarily that thing that's wrong is they say this. They say something along the lines of, and now this is wrong, right? They say, there is a 95% probability that the population mean mu is in the interval that we just calculated out. The only thing that they're really changing out is the word probability with the word confident. That small change makes the answer completely wrong. And here's why. If I ask you, if I give you, let's take this as a quick aside. If I give you the interval from 0 to 5, is the number 4 in that interval? Yeah, the number 4 is definitely in somewhere between 0 and 5, right? It's 100% in there. There's no question about it. It's most certainly in that interval. If I told you that there's only a 90% chance that 4 is in that interval, then that's saying then that there's a 10% chance that it's not. Well, that's just not true, right? We know back from like elementary school that 4 is definitely in that interval, right? Does that make sense? So therefore, if I tell you that there's only a 90% probability that 4 is in this interval, that statement is 100% inaccurate, right? Does that make sense? So what we're saying here is this. If we go back now to the very, very first page of the notes, and this is why I belabored it so long whenever we were going over it. If we go back to that first example that we got, what we're trying to come up with is an estimate for an interval where we believe that mu is in here. Well, there's only one thing that we can say for certain, and that is this. Either mu is in here or it's not in here. We don't know if it is or if it's not, but we think that it is, and we're 95% confident that it is. You guys see where the difference is now? Either mu is definitely in here or it's definitely not. We don't know that whether it is or not, so therefore we can only come up with a certain level of confidence. Again, if we blow this confidence interval wide open from 5 feet to 7 feet, now what we can say is mu is definitely in there or it's definitely not. Nothing's changed about that. But now we're just much more confident that it is in there. Right? Is everybody good with that? The only thing that we keep doing whenever we're coming up with these confidence intervals is we're coming up with an interval. We have no idea whether mu is in there or mu is not in there. It's either definitely in there or it's definitely not. We can only express a confidence in our estimate. So therefore, if we go back to this interpretation now, it's one thing to say that we're 95% confident that mu is in there. It would be completely wrong to say that there's a 95% probability that mu is in there. Because mu is either in there or it's not. It's a very, very subtle difference. But that subtle difference is often missed by people. So therefore I say, if you have to provide an interpretation, use this as your interpretation. Swap out what's in the boxes, and then you're going to be good to go. Okay? All right. Take maybe 3 or 4 minutes for yourself and see if you can do number 2 completely by yourself.
answer your question earlier? I just remember that.
Yes.
Okay.
So when it comes to like switching out that one,
Mm-hmm.
I get everything else, but like, would you put population sample mean?
No, so the only thing that we're always trying to do is we're trying to find these for the population mean.
Okay.
Just like down here to
This one's still the population mean.
for the mean. Yeah, exactly. This is still mean. The only time that this would not be mean is we would swap in their proportion p, and that's just when we get to proportions. It's either always going to be population mean or population proportion p. Those are our only two options for this class.
Makes a lot of sense.
Cool.
Thank you.
Sure. Does anybody need a little extra time? Who here thinks that they have the correct answer? Who here thinks that they at least knew how to start? And who here was just like, those were the most agonizing 3 minutes of my life? Nobody. Okay, good.
Good. At least, like in my large classes, I always get the person in the back, like, right. Like, yeah, we're good together. It's okay. All right. In a study of amount of time required for room service delivery at a newly opened Radisson hotel, that so far is completely pointless, 45 deliveries had a mean time of 24.2 minutes and a standard deviation of 8.7.
All right. So this portion right here, this is important, right? And I'm trying to point this out to show you guys that whenever you're dealing with word problems, we're still just trying to boil it down to like the types of questions that we had for number one. Then we're asked to find what is a 90% confidence interval for the mean time of deliveries, and then interpret our results. All right. So one of the things that I usually like to do whenever we're doing these types of problems, especially now that we're getting into like the word problems type stuff, is just like I've been doing all semester, try to identify like a buzzword that we can use to say, hey, this is when I need to do this stuff that we're learning right now.
Again, whenever you're taking a test, it's never going to say, hey, on the chapter 7 question,
So how can we identify that it's a chapter 7 question? What do you guys think the buzzword is? Confidence interval. All right, we're trying to do confidence intervals, right? Confidence intervals. All right, now that we're trying to do a confidence interval, what's always our first step whenever we do confidence intervals? Say again? Not quite. Good. We're going to ask those two questions. Is n greater than or equal to 30, and is sigma known? That's always going to be our first two questions. In this problem, how big is our sample size? 45, so we're going to answer yes to this. Again, it's sufficient to just answer yes to one of those questions. And if we answer yes to at least one of these questions, we know that we're going to be using what? Z values. Cool. All right. But I want to also practice this one right here, because had we said no to this one, we still want to see if we say yes to this one. So let's practice this one too. Is sigma known? No. Why is sigma not known? It doesn't say it's for a population. We're specifically only talking about 45 deliveries. I think that everybody would agree that at a Radisson hotel, they deliver many, many more times than only 45 deliveries, right? So we're only looking at a snapshot of 45, so therefore here we're answering no. Again, we only have to answer yes to one of these, so nevertheless, we're still going to be using Z values. Everybody good with this? Now, if we want to write down the confidence interval formula, we're still looking at means. So since we're looking at means, we're still going to use X bar as our point estimate. We're going to add and subtract our margin of error from it. And now we know that our margin of error has to be a Z value, so that's why we have a Z right here. We're going to have alpha divided by 2. We're always going to have square root of n down here in our denominator, but now what's the symbol that goes up in our numerator? S. We do not know sigma. Sigma is unknown, so therefore we can't use sigma right here. We have to use S. Even if you botch that portion of it, where you're saying that this right here is sigma, not S, it's no big deal because we're always just putting it up in the numerator, right? The only portion where it really becomes important that we answered no right here is if we answered no to both of these. And if we answer no to both of these, again, what do we use? T values. All right, and that's something that we're going to get to next class. Everybody good so far with this setup? If you're good with this setup, then I think you guys are good to go with this problem, because what is X bar equal to? 24.2 plus or minus. We'll skip Z here for a second. What is S equal to? And what is our sample size?
Square root of 45.
Awesome. Good. 45, right? So we're going to put square root of 45. That looks ugly. Let me correct that. 45. Everybody good with this so far? Now, again, the only portion that's missing is what we practiced several times at the beginning of class today. That's why we belabored it at the beginning of class today. For Z value, Z sub alpha divided by 2. What's our confidence level in this problem? 90%, so therefore alpha is equal to 10%, therefore alpha divided by 2 is 5% or 0.05. The Z value that corresponds to 0.05 is 1.645. Everybody good with 1.645? Anybody want me to go over that one more time? The reason why I keep going through that process, and I know it's just a quick, simple math process, but it becomes extremely important in Chapter 8, in the next chapter that we do. That's why I'm always asking you guys, what's the confidence level, then what's alpha, and what's alpha divided by 2. I know you guys can do that stuff in your head. But in Chapter 8, what we're going to start using is sometimes we're going to be using just alpha, and sometimes we're going to be using alpha divided by 2. So that's why we're going through the process of making sure you guys understand what the difference is between alpha and alpha divided by 2, because sometimes we're going to be using one versus the other. All right. If we do this now, then the arithmetic that we would do would give us 22.07 to 26.33. Everybody good with this? Then the last thing that we just need is our interpretation. Our interpretation says that, what does our interpretation say?
Your 90% confidence population. So just instead of population, you would just put mean sample.
Great question. That's why I asked you guys to dictate to me. If we go back to what we said in the previous problem,
Was population in the box? No, population's not in the box. Therefore, the word population is never something that you're going to swap out.
Okay.
Think about it like this, right? That's just a quick and easy method. Think about it like this. We're always using something from the sample to estimate something from the population. That's the picture that we drew at the beginning of chapter 7. Right? You guys remember that? Like, we had a population, we took a sample, we calculated something out from the sample, and we used something from the sample to estimate the population. You guys remember that picture? We're always trying to estimate a characteristic from the population. We're never trying to estimate a characteristic from a sample. Why do we not have to estimate a characteristic from the sample? Say what? Sure you do. Why do we never have to estimate a characteristic from a sample? You guys know this. I know you know. Don't overthink this. So let's put it into like an everyday problem, then it's going to be super straightforward. I come to you and I ask you, tell me what the average height is of all students at UNCC. To which you go, I don't know, right? So then what do? You say, hey, all right, I took statistics. I'm going to go out and I'm going to take a sample, right? My sample is going to be 30 people because now I know that 30 people is going to satisfy the central limit theorem. So I'm going to be good to go. We're going to see that that's not 100% accurate, but we'll stick with it for now, right? 30 people. Now if you have 30 people, do I have to ask you to estimate their heights? No. Why don't you want to estimate their height? Because you took a group of people for which you can calculate that. Right? Is everybody good with that? So we're always going to estimate something from the population because the population could potentially be huge. But am I ever going to ask you to estimate something from a sample? No, because then we're defeating the point of taking a sample. You're taking a sample because you can calculate stuff. So therefore, going now back to your question, we're always going to say that we're confident about something for the population. We're never going to say something about the sample. That's why population is not included in the box. So the quick and easy was population isn't in the box, but that's the reason why population is not in the box. So that the population mean mu, the only thing that we're ever going to change out is the mean mu portion of it once we get to where we're dealing with proportions, when we're no longer dealing with averages. Mean mu is in the interval, what we just calculated out. I know I have atrocious handwriting, but I think everybody's good with what I'm writing up here. All right. What do you guys think is going to change about the problems that we're going to start with at the beginning of tomorrow's class? T's. And how are we going to get to T's?
Being less than.
We're going to have a sample size that's less than 30. That's the only way that we can get down to T's. And then we're going to either know sigma or we're not going to know sigma. And whenever we don't know sigma, we're going to use T's. All right. I'll see you guys tomorrow.